Welcome back to our channel Sankalp Study Success. Today in this lecture we are going to study about the fundamental theorem of arithmetic. Here in this lecture we are going to mainly concentrate on what is the fundamental theorem and how to find out the GCD using prime factorization method, and also we are going to see about how to find out the LCM using prime factorization method in this lecture. So let's go into the first theorem, which is about fundamental theorem of arithmetic. Here it mainly concentrates on any integer which is greater than 1. That is, any number n which is greater than 1, you can express this number uniquely as product of primes. That means what? N is equals to p1, p2, p3, p4 and so on, pn. We are expressing a number in the form of product of primes. We are expressing in the form of product of primes. Here the theorem also states that every integer which is greater than 1 can be uniquely expressed as product of primes up to the order of the factors. Now consider n is equals to p1, p2 and so on up to pu. That means I have considered here n. You can consider any variable, that is pu, and if n is equals to p1, p2 up to pu, and also n is equals to q1, q2 up to qv. That means you are expressing the same number n here and also here, but in the form of p's and q's. That means you have written two factorizations here as a product of primes. That means what? This is equal to this. When both the LHS are equal, then both the RHS are also equal, right? So here u is equals to v. That's the reason u is equals to v. And you can also express it as pi is equals to qi, correct? Because these are the products by considering the variable p. These are the products by considering the variable q. So you can also say it as pi is equals to qi. Now, how do we prove this? That means, how can you prove whether an integer is expressed in the form of product of primes? Let us see how we can prove this. Here we divide the proof into two parts. That means first step and the second step. In the step-by-step procedure we need to prove the theorem. So let's see. In the first step you have to consider S of n, which denotes the statement. S of n is just a statement. That means n can be expressed as product of primes. That means if you consider if n is equals to 2, then 2 is a prime number, right? So you can express 2 is a prime number, so you can express just 2 as 2 only. So you are expressing, that means S of 2 is true here. This is the first step. Now coming to the inductive hypothesis, we are proving the theorem using mathematical induction, right? Mathematical induction. So in the first step you have taken that 2 is a prime. So in the second step, by using inductive hypothesis, see what you will do here. You will consider S of 2, S of 3 and so on up to S of k. That means you are proving for k here. In the next step you will prove for k plus 1. So when you are proving for k, it can be expressed as, you should prove that these should be expressed as product of primes. So to prove that S of k can also be expressed as product of primes, right? If it is a prime number, then we'll write the number as it is. If it is a composite number, you can express it as product of primes. Now coming to the inductive step, you have to prove for S of k plus 1. See here. To prove that S of k plus 1 is true, what you need to do, k plus 1 should be expressed in the terms of product of primes. So if k plus 1 is prime, then we will express it as k plus 1 only. But if k plus 1 if is composite, if it is a composite number, then there exist an integers u and v. Here this is the important step where k plus 1 is equals to uv. That means what? You are expressing this composite number in the form of product of primes. That means u into v. It is nothing but u into v. If what is u and what is v? Both are, we are expressing the form of product of primes. That means u is a product of prime and v is a product of prime. So if you take u is equals to p1, p2 and so on up to pi, and v as q1, q2 and so on up to qi, then you can say that p1, p2 and so on pi and q1, q2 and so on qi are prime numbers. So hence p of k plus 1 is also true. Okay, clear? So by using mathematical induction, what we have proved just now, a number which is greater than 1 can be expressed as product of primes. Okay, this theorem proves that any number can be expressed as product of primes. So clear? Now we are going into the next one, which is the exact definition, fundamental theorem of arithmetic. What does it say? Just now we have proven it. Every integer which is greater than 1 can be factored uniquely into product of primes. This is the most important term, product of primes. You need to express in terms of product of primes. Now let's see an example so that you can understand much better. Prime factorization of 250 and 400. How do you factorize 250? We need to express 250 in a product of primes. So by using prime factorization method, that is, let's divide, the smallest prime number is 2. So let's take 2. 2 ones 2 and 2 twos are 4. 2 fives are 10. So that means what? 125 times will give 250. Now let's take 5. Because the last digit is 5, so it is divisible by 5. So now let's take 5. 5 2 times is 10. You will get 2 here. 5 5s are 25. Now we all know fifth table, 5 5s are 25 and 5 1s are 5. So that means what? 250 is expressed as 2 into 5 into 5 into 5. That means what? 2 into 5 to the power of 3. That means there are 3 5s here. So 2 into 5 to the power of 3. So you can express 250 as product of primes as 2 into 5 to the power of 3. This is the prime factorization of 250. In a similar way, let us see the prime factorization of 400. It is divisible by 2. So let's go with the 2. 2 twos are 4. 2 zeros here. Again it is divisible by 2. 2 ones are 2. Again it is divisible by 2. 2 fives are 10 and 1 0. 2 twos are 4. Here we will get 1 and 2 fives are 10. Here it is divisible by 5. 5 fives are 5 and 5 ones are 1. So you can express 400 as product of primes as we are having 4 2's here. So 2 into 2 into 2 into 2 and 5 into 5. So on further simplification, you will get 2 to the power of 4 into 5 to the power of 2, that is 5 square. So 400 can be expressed as product of primes in the form of 2 to the power of 4 into 5 square. So I think you all are clear by how to do the prime factorization of any number, correct? So you can try these. You can find the prime factorization of 100, 289 and 630 separately. You can find it out, and you can also find the prime factorization of 864, and you can also find this. So by solving all these problems, you will become much more clear in this topic. So let's go into the next topic, which is canonical decomposition, which is also similar to the prime factorization method only. So we will see what is canonical decomposition and we'll solve one problem to get more clarity on this topic. Here comes canonical decomposition of positive integer n. Here we are considering an integer n, which is of the form a is equals to p1 to the power of a1, p2 to the power of a2, and so on, pk to the power of ak. That means what? We are expressing a number in the form of product of primes only, because p1, p2 and so on, pk are nothing but the product of prime numbers. But these prime numbers we are also having powers to those prime numbers, that is a1, a2 and so on up to ak are the exponents. Those are nothing but the powers. So if you express any number in this format, that means it is nothing but the canonical decomposition. So you can solve this canonical decomposition in the two steps. That means two different methods. The first method involves all the prime factors beginning with the smallest prime. That means what? What is the smallest prime? Beginning with 2. Beginning with 2, you can find all the prime factors of the given number. That is the first method. And what is the second method, which is more efficient method? Here you are going to split n as product of two positive integers. That means what? We'll solve a problem so that you will get more clarity. Here, canonical decomposition of 2520. We are taking a number 2520. First, we will solve it in the first method only. 2520, you can express it as 2 into 1260 by using prime factorization. That means 2 is a factor. Now, if you further write it as 2 into 630, this you can write it as 2 into 630. Now again, 2 into 2 into 630 can be written as 2 into 315, correct? By using prime factorization only. 2 into 2 into 2 into, again 315 is divisible by 5. So we'll write 5 into 63. Sixty-three can be written as 7 into 9, correct? Because 7 is a prime number. Now 9 can be written as 3 into 3. We got all the prime numbers here. So how do we express it as? There are 3 2's. So 2 to the power of 3 into, there is only one 5. So 5 to the power of 1 into 7 to the power of 1 into 3 square. This is the first method by which canonical decomposition of 2520 can be solved. Okay. Now we can also follow the second method, which is, let me erase it so that we can go with the second method. Okay, what is the second method? Second method is the most efficient method, which we have seen already, which we have learned in the previous slide. Here comes the second method. What can we solve in the second method? Here, 2520, you have to decompose. No need to decompose in the form of product of primes. You can decompose it as 40 into 63, correct? You can decompose it as 40 into 63. Now, this 40 can be written as 4 into 10. Now, this 63 can be written as 7 into 9. Because 7 9s it is 63 and 4 10s it is 40. Now, how can you write 4? It is of the form 2 into 2. We'll get it 4, right? Now 10. 10 it can be written as 2 into 5. Now, 7 is a prime number, so you cannot write anything. Just write it as it is. Now 9. 9 is not a prime number. 9 can be written as 3 into 3. So now, how can you write it? It is nothing, just again we got the same thing which we got in the first method, that is 2 to the power of 3 into 5 to the power of 1 into 7 to the power of 1 and 3 to the power of 2. That means 3 square, right? So we got the same answer when you have done it using the prime factorization method of the first method and the second method of just decomposing it into two numbers. Okay, now we are going to draw a factor tree for this decomposition. Factor tree. What is a factor tree? We have solved it for 2520, correct? So first you will write 2520. Then how did you decompose into two numbers 40 and 63? You have to write it like this. Now again 40 was divided as 4 tens of 40, right? And 63 was divided as 7 nines. So the way how you are decomposing, in the same manner you need to represent it in the factor tree. Now 4 is decomposed as 2 into 2. 10 is decomposed as 2 into 5. 7 is same as 7 only. You have just copied down, you have just written it because you can't express it anymore because it is a prime number. 9 can be expressed as 3 and 3. So this is the factor tree for the canonical decomposition. That means the canonical decomposition, the way you are decomposing each number into its prime numbers. In the same manner, you have to represent it in the factor tree. Okay, clear? Now, there is a small note which are here we have some of the important points. By using canonical decomposition, you can find out GCD of two numbers as well as the LCM of two numbers. See here, we are finding the GCD and we are finding the LCM of two numbers. How are we going to find GCD and LCM? That is the main question. Here, GCD of two numbers is P are nothing but the product of primes which you express each number. When you express in product of primes, you will get P1, P2 and P3 and so on. So, there are two numbers M and N. Let us consider these same numbers which are here, M and N. M can be expressed as P1 power A1, P2 power A2 and so on like this. Pu power Au. In the same way, N is expressed as P1 power B1, P2 power B2, P3 power B3 and so on up to PV power BV, correct? So now, what is the GCD generally? We are going to find the common divisors in both M and N, correct? In both M and N, you have to find the common divisors. Here, you have to find the common divisors. So, for the common divisors, you will be having the different powers. So, you have to take the minimum of the powers and then multiply, then you will get GCD. In the same manner, if you take the maximum of the powers and multiply the numbers, then you will get the LCM of two numbers. So to get the more clarity, we'll go with an example by using prime factorization method to find GCD of 18 and 30. So how do you find the GCD of 18 and 30 using the prime factorization method? That is nothing but the canonical decomposition also. You can get the question in the form of use canonical decomposition. Use canonical decomposition to find GCD of again 18 and 30. Okay, you got it right. Both the numbers are one and the same. Okay, now both the questions are one and the same, sorry. So let us see how to solve this question. What is given? First we need to write the given data. Given 18 and 30. So how do you express 18? 2 into 9. Again 2 into 9 can be expressed as 3 into 3, correct? Now 30 can be expressed as 3 into 10. Again 10 can be expressed as 2 into 5. So what happens is, here we need to find we have to write it in powers, right? 2 power 1, 3 square. Here, how do we write? P power 1, 2 power 1 and 5 power 1. There are only each one of the one term. So, now you have to find the common divisor. What are the common factors? What are the common numbers involved? Here, GCD of 18, 30. How do you find? It is 2 to the power of minimum of 1, 1. That means what? Here we have 2, which is a common. Here we have 2. So the 2 is in common. What are the powers of 2? 1 and 1. You need to find the minimum of 1 and 1 into, you have 3, right? 3 is also in common. 3 and 3 here. So minimum of 2, 1. So 2 power. What is minimum of 1, 1? 1. 1 is the minimum into 3 power. What is the minimum of 2, 1? 1, right? What is the product of this? 3 2 is 6. So the GCD of 18 and 30 is 6. Okay, clear? First you need to find the canonical decomposition of both 18 and 30. Then you have to find what is in common. What are the numbers which are in common and their powers, minimum of their powers you need to multiply in order to get the GCD of two numbers. Now let us see how to find the LCM of two numbers, which is 119 and 544. How do you find the LCM? Let us see here. Given data is 119 and 544. So how can you write 119 and 544? First of all, you need to find the canonical decomposition. 119 can be written as 2 to the power of 0 into 7 to the power of 1 into 20 to the power of 1. This is the canonical decomposition of 119 and 544. What is the canonical decomposition of 544? It is 2 to the power of 5 into 7 to the power of 0 into 17 to the power of 1. Okay, this is the canonical decomposition of 544. Now you need to find the LCM of 119 and 544. That means what? You need to find the maximum powers of the common factors, that is 2 power max of 0, 5 into 7 power max of 1, 0 into 17 to the power of max 17 power of max of 1, 1. So max of 0, 5 is 5, right? 5. 7 to the power of max of 1, 0 is 1 and 17 to the power of 1. So 2 to the power of 5 is 32, correct? Into 7 into 17. So if you multiply all this, you will get 3808. That means 3808 is the LCM of 119, 544. Is it clear how to find the LCM of two numbers using the canonical decomposition, or you can also say it as prime factorization, and also how to find the GCD of two numbers by using canonical decomposition or prime factorization method. So these two are the most important, so you have to concentrate on how to finding the GCD and LCM. Thank you for watching the video. Let's meet in the next lecture.